Good evening, everyone. Today we are discussing our practice paper 90. Okay, so after the evaluation test paper discussion, we are back again with our practice paper discussions. Okay, so in this paper we have 10 MCQs, which are from Unit 1 to Unit 4. Okay, up to gases. Nowadays we are doing gases in our 2027 class now. And then, in addition to that, our plan was to discuss these past paper chemical calculation essay questions. Okay, so we did two of them in the class, and we have to do the 2021 and 2022 A-level chemical calculation essays. Okay, so today we will start the class from those essay questions, and after that we will move into our MCQ discussion. Now, this is the first question we are going to discuss. It is from 2021 A-level essay paper. Right, so the question is asking that there is a mixture called X which contain two compounds, okay, aluminium sulfide and ferric sulfide, okay, Al2S3 and Fe2S3. So the following procedure was carried out to calculate the mass percentage of Al2S3 and Fe2S3 in X. Okay, so that's the target. And it is telling when a mass of M of the mixture X was heated at high temperature under hydrogen gas, Al2S3 remains unchanged, but Fe2S3 converted into iron. So now the thing is this now, okay? So by taking several chemical reactions, they are explaining how to find these mass percentages, at least using two set of reactions. Because what we have seen in these mixture type questions, we are finally going to form two simultaneous equations. Okay, in order to do that, we need at least two experiments, two reactions we need. Okay, so here they are starting the reaction, starting the question by telling this mixture is heated with hydrogen. So during that process, okay, Al2S3 is not going to do anything, but Fe2S3 converted to Fe. Okay, so we'll make a small diagram for that one. So now our mixture contain Al2S3 and Fe2S3, right? Now, first of all, we are taking m gram mass, and then we are heating that one with Al2S3 is heating with hydrogen, and Fe2S3 is heated with hydrogen. And it says when it is heated with Al2S3, nothing will happen. And but with Fe2S3, it says it is converted to Fe. So now they haven't tell what are the other products. Okay, what are the other products? But however, they tell us the final mass of the mixture obtained is 0.824. 0.824. So nothing will happen. That means Al2S3 is there. Now this is the process that will happen. So once it is reacted with hydrogen, Al2S3, nothing will happen. But Fe2S3 is converted to Fe. Right, so we need to balance this. So now take a guess what would happen to this other element, sulfur. And it is reacting with hydrogen. So it should form some compound that contains sulfur and hydrogen. So it must be H2S. Because this will be a redox reaction. Okay, if you think it further, you can understand. Iron is basically reducing here from +3 to 0. So then something else should undergo oxidation. So what is undergoing oxidation here is hydrogen. Hydrogen is undergoing oxidation from 0 to +1. Understood? So in that way, you can think what is happening. Okay, you can realize these are the correct products. And then let's balance this on using inspection method. Okay, so you had two iron atoms, ions earlier, and they must be converting to 2Fe. And there were three sulfide ions, so they will form 3H2S. So to do that, you need 3H2. Okay, so in this question, they are not expecting you to balance this reaction, but however, okay, since we are doing a discussion here, let's balance it. Okay, right. So what you need to do next is this. Right now, for a mixture of questions, mixture of two substances, you have to assume that from one substance there are X moles. From the other substance, you have to say there are Y moles. So there are many methods you can do this question, okay? But the most easy way is assuming one compound's moles as X and the other compound's moles as Y, okay? So now let's say you are having X moles of this compound and you are having Y moles of this compound, okay? So then here you had X and it was not changed, no? So that same X moles are there, right? And from Fe to S3 you had Y moles, but after the reaction you can see the stoichiometry ratio, you will get 2Y of iron. Understood? 2Y, because the ratio is 1:2. Okay, so that number of moles sum is, if you turn it into grams, it will be 0.824, right? So now let's, in the question, it is telling actually the relative atomic masses. So we can find out the molar masses of these compounds, right? So let's find out the molar mass of Al2S3 first. Al2S3, so aluminum is 27. So 27 times 2, that is 54. And then sulfur, 32. 32 times 3, it is 96. So if you add them, you will get 150. 150. Okay. So 150 is the molar mass. So you can write like this. Mass of Al2S3 plus mass of Fe is equal to this number, no? So now let's replace this one. So mass of Al2S3 you can write 150x, because why? Moles, number of moles are equal to mass over molar mass. So if you subject mass, it is moles into molar mass. Okay, so you have X moles and molar mass is 150. Is that clear? So in that way you can find out the number of moles. So the mass of Fe is 2Y into 56. 56 is the molar mass of iron. Okay, so if you simplify this one, you can write 112Y. So is that clear now? This is our first equation. Okay, this is our first equation. I'll show you the question again and I'll remind you that theory part I just told you. So the molar masses are given somewhere, see? Aluminium 57, sulfur 32 and iron 56 is given. So no problem with that, okay? Right, so that's it about the first part. We got one equation. So now our task is to find another equation, okay? Now let's see how to do that. So it's saying another mass M of the mixture X was heated at high temperature in air. High temperature in air. Air means air contains several gases, no? Atmospheric air. So the only possible gas that can be reacting here is oxygen, because nitrogen is normally considered to be an inert gas. So the reactive gas here is oxygen. So that means oxygen can react with these two. So you can see that is true, because sulfur is ultimately converted to SO2. That means sulfur has combined with oxygen. So the reactive gas in air must be oxygen. Think, okay, think. They are not telling everything directly in essay questions. You have to understand by reading the question. That's a skill you need to develop. Okay, I'm sure you will get there. We'll slowly do these essay questions and it will good for our practice. Okay, and we have the recording also, so you can refer that again. Right, so anyway, Al2S3 and Fe2S3 is converting to SO2 gas. Okay, so what will happen to their metal? So metal also should go to the oxide, but here they are not expecting you to write that. You can see in the questions also, they are asking you to write the reaction between Fe2S3 and hydrogen gas. Okay, I said earlier it is not needed, but you can see it is asked here, okay? So that reaction we wrote, okay? And the other reaction they are expecting is the reaction between SO2 and hydrogen peroxide. So that means they are not expecting you to write the reaction between aluminium sulfide, ferric sulfide with oxygen. Okay, so but however you need to understand, all the sulfur atoms that are containing here are converting to SO2. Okay, all the sulfur atoms are converting to SO2. So you write that again. We have Al2S3, which is reacting with O2. So let's write like this. Since you are not balancing it, I write oxygen on the top of arrow. Okay, so it's converting to SO2. Right, so basically it is giving 3 SO2 because there are 3 sulfur atoms. So now let's say you had X moles, you will get 3X moles. 3X moles. So here also they are moles, okay? So when you are writing the review, add them. And then the next one you have Fe2S3. So this one is also reacting with oxygen to give 3 SO2. Let's say you had Y moles of this one, so you will get 3 Y moles. 3 Y moles. So total SO2 moles are now what? You have 3x plus 3y moles of SO2. Okay, so SO2 you have 3x plus 3y, or you can say 3 times x plus y. Moles are there from SO2. Is that clear? And then what this SO2 is doing? Let's go and check the question again. It says this SO2 gas was bubbled through the solution of H2O2, hydrogen peroxide, and oxidized to H2SO4, and which is the only product. So that statement is a very good one, because we know that we need to balance this one using inspection method. Okay, so it says when it is reacted with hydrogen peroxide, only product is H2SO4. Okay, so no other product. So you can easily balance by seeing this one. So actually it is balanced, no? See, 1 sulfur, 4 oxygen, and 2 hydrogen. So it's balanced. That means 1 of this one reacted, 1 of this to give 1 of sulfuric. So moles of sulfuric is also what? 3 times x plus y. 3 times x plus y. Okay. So now the next part. Okay. When this entire solution was titrated with standard 1 mole per decimeter cube sodium hydroxide solution in the presence of phenolphthalein indicator, you can just treat it as a normal acid base indicator. Don't worry about that one. So however, they are reacting, and the burette reading was 36 cubic centimeters. Okay, so 1m36. Now this sulfuric is the entire solution. The entire solution is titrated with sodium hydroxide. Sodium hydroxide. Sodium hydroxide concentration is 1 mole per decimeter cube, and 36 cubic centimeters are consumed. Now, what is the reaction happening here? H2SO4 is a dibasic acid. That means it can release 2 H pluses, and it reacts with sodium hydroxide. And this is acid-base reaction. You can balance. The salt is Na2SO4, and it is forming 2 water also. Okay, 2H2O. Can't see, right? Plus 2H2O. This is the balance reaction. And here you have right 2. So that means they reacting 1:2 ratio. 1:2 ratio. Now you can see the whole question is there in the board. You have the reactions, you have the XY symbols, right? Now only thing we have to do is simplifying this one. Now we need another simultaneous equation to go along with this one. So now let's see how to form that. So from these two data, we can find the moles of sodium hydroxide. If you know the moles of sodium hydroxide, then half of that will be sulfuric. That means this. Okay, in other words, we can say like this too. This is 3 times x plus y. Then our sodium hydroxide should be what? 2 times like that. No? That means 6 times x plus y. which is equal to this number of moles. Okay, so now our second equation will be, let's simplify. Let's write that second equation. Here we can just simplify the moles in this side. Moles of sodium hydroxide is equal to concentration into volume. 1 mole per decimeter cube into 36 into 10 to the power minus 3 decimeter cube. So that means you can write 0.036 moles, or you can use scientific notation if you want, right? And the final equation is 0.036 is equal to 6 times x plus y. And this is our second equation. Can you see the two equations? So by simplifying them, we can find out x and y, which means the number of moles of the initial compound. Okay, then we can easily go to the mass percentage. So how do we find the mass percentage? Mass percentage, how do we find? Finally, we are going to find it now. Mass percentage of, let's say, Al2S3. What should we do? Get the mass of Al2S3 and divide by the total mass, which means the sum of the two compounds, and then put it into 100%. This is the summary of the question. Okay, is that clear, Lama? Any doubts, any questions? You can ask anything. Okay, so look at the questions they have asked. The balanced chemical equation between Fe2S3 and hydrogen. You can write it. Then the balanced chemical equation for the SO2 and H2O2. We did that too. And then calculate the mass percentage of these two compounds. Yeah, then we can answer the final question also before going into the simplifications. It is asking if the above titration is carried out using methyl orange as the indicator instead of phenolphthalein. Would there be a change of burette reading? So your answer should be no. Okay, so there will be no change of burette reading. You haven't done the acid-base indicators yet. Yeah, it will be discussed in unit 12. So until that, you can write this statement. Okay, for any strong acid, strong base titration. Okay, for any strong acid, strong base titration, any indicator can be used. Okay, for any strong acid, strong base titration, any indicator can be used. Okay, so it doesn't matter whether the indicator is phenolphthalein or methyl orange. Still, it will give you the same burette reading if the reacting acids and bases are strong. Okay, so that's the point. Try to understand that one and make a small note on that too. So if the acid or base is weak, then it is affected by the indicator. Okay, so I'm not going to talk about that one now. So it is a separate lesson. So let's look at that one later. Okay, for now, for the sake of this question, you can write. It is kind of okay. It's no problem with the type of the indicator. Okay, so now let's go and check the answers of the question. Okay, right. Right, so now we have the answers. I have the method here. So we can start by simplifying these two equations. So how do we simplify a simultaneous equation? That is a question we need to address, right? So we need to cancel one of these two. If I expanded this, 0.036 equals 6x and 6y. I forgot that part. 6x plus 6y. So then if I want to cancel, let's cancel y. That is easier to do. Then what I need to do is multiplying this 6x by some number in order to equal it to 150. So can I do that one? 150, is it divisible by 6? Yes, no? 12 and 30. Yeah, 25. 25. So let's multiply this one by 25. The second equation. Second equation multiplied by 25. So 0.036 into 25. 25 means 100 over 4. So it's far more easy to divide like this 0.009 into 100. So 0.9. 0.90 is equal to, we are multiplying by 25. So 150x and 150y. So this is our third equation. Now let's subtract first equation from the third one. Okay, so then you will left with 0.076 equals to 150x is cancelled. Okay, so then 112 means 48, 38. 38y. So then y is equal to this divisible from 38, 0.002 moles. Okay, so then we know this thing, right? So I could earlier simplify this also, not to be much more easier. Anyway, here this one was 0.036, and if I cut this, it will be 0.006 equal to x and y. No? So then we can find out x by subtracting 0.006, 0.002. So it's going to be this moles. This is the value of x. So like that you can simplify and find out. So just do the maths part carefully. Okay, then you can avoid the problems, right? And then after finding the moles, we can do this simplification. So the molar mass of Al2S3 we found earlier, it is 150. Okay, so let's see how to do this one. Moles 0.04, no? 0.004 into 150. That is the mass of Al2S3. And the total mass, again, I need the other mass also. Yes. Anyway, so what is the molar mass of Fe2S3? 56 into 2, 112. Sulfur 3 times 3296. And 8, 0, 1, 2. 208. 208. Okay. So now the simplification part is the difficult one. No? So we can find out mass of Fe, mass of Fe2S3 by multiplying 0.002 by 112 and 96. 112, 96. Yeah, 208. 208. So it's going to be 416, 0.416 grams. And the other one is mass of Al2S3. Just multiply 0.004 by 150. So 600, 0.600 grams. Okay, so then we can substitute here and do the simplification. Yeah. Yeah, only the space problem is there anyway. I'll get some space from the above. So now actually we are in the last bit of the question. So I hope you understood this thing up to here. So look at the question carefully, Lamai, and see whether you have any doubts in the process. So I'll show you the last simplification. Give me a minute, okay? And here, if I find the Al2S3 mass percentage, what should we do? Get this 0.6 divide by the total mass, which is if you add them at these two, you will get 1.016 and into 100%. It's almost 1. So let's see the marking scheme whether they have given marks for 60%. Or if not, we have to do the full simplification, okay? And the other one must be 40%. Okay, so now I have the marking scheme. Let's check the answer they have given us. Yeah, our masses are, they all correct. So it is going to be, yeah, 59.59%, not the 60%, okay? Should be 59%. And the other one is 41%. So if you do the simplification, I just rounded off now. So if without doing that, you have to divide 60 from 1.016. Yes, it is 59%. Yeah, don't worry, you will lose only fewer marks for the final answer, okay? So because this one we can't do, normally we have to use a logbook to do this simplification, the final one. If there are only two compounds now, if you found one, then other one must be Fe2S3. Also, you have to show the simplification, and finally the answer will be 41%. Okay, so that's it for the first question. I hope you all understood. Okay, so if I repeat the method again, so what is the method? There is a mixture that contain Fe2S3 and Al2S3, right? So at the beginning, we label their moles to be X and Y. Okay, I said again earlier, this is just one method. If you check the marking scheme, you will see there are other methods also. You can start by assuming the mass of this one as M, other one is M1 and M2, like that. There are many methods to do. Okay, but usually the easiest way of going with the number of moles, assuming it as X and Y. And there are two set of reactions. First one is telling that Al2S3 and Fe2S3 are reacting with hydrogen. So in that reaction, they have given you the final mass. Okay, so only iron is reacting properly. So then you can get this equation. Okay, and if you get the molar masses, you will get this equation. First one, the mass of Fe2, Fen, Al2S3 is equal to 0.824. And the other one, they says it is reacting with oxygen and finally releasing SO2. That SO2 is converted to H2SO4 and then it is reacted with sodium hydroxide. Okay, and sodium hydroxide moles you can find by using their concentration and volume, and that is equal to 6 times X plus Y because we made it from here. Okay, and then finally we can simplify the two equations using simultaneous method, and then you will get X moles as 0.004, Y moles as 0.002. Then since they are asking the mass percentages, we need the masses of them, and then apply like this. Okay, I did the simplification here. You will get 59% for the aluminum sulfide mass percentage and 41% for the ferric sulfide mass percentage. Okay, so that's the method. I hope it is clear. Hope it is clear. Right. You have to be careful with the simplifications. Okay, Lama? Right. Now, let's go and check the second question. This is from 2022 A-level paper. An iron ore, Xn, contains FeO and Fe2O3, an inert substance. Following experimental procedure was used to determine the mass percentage of FeO and Fe2O3. First, it says we are taking 0.48 grams of X. 0.48 grams of X. And it was dissolved in 10 cubic centimeters of concentrated acid. And this solution was filtered to remove insoluble matter. Thereafter diluted to 50 using distilled water. Right. So that is added to 10 cubic centimeters of conc acid. That means whatever the compound is there, it will be dissoluble. And then it is diluted by adding water. Now the contents are there in 50 cubic centimeter volume. Okay. This entire diluted solution was titrated with 0.02 potassium permanganate. Okay, so now that means this is transferred to a titration flask, 50 cubic centimeters of the solution. and it is titrated with KMnO4. KMnO4. The question says KMnO4 concentration is 0.02. And do they have tell us the volume? The titration, the reading at the endpoint was 20. Yes, the volume is 20 cubic centimeters. And then look at the next thing, the pH of the entire solution obtained after the titration was raised to 12 pH 12. Okay, so after the titration, you will get a solution. Okay, so that solution pH value increased to 12. pH increased to 12. That means it has made basic, no? Okay, so then it is telling at this stage, the metal ions in the solution were precipitated as their hydroxides. So the precipitate was filtered and dried until a constant mass was obtained. The mass of the precipitate obtained was 0.5706. Okay, so then the precipitate that you are getting here, 0.5706. This is the gram value of that part. So again, you can see two ends are there. That means they are asking you to get the answer using simultaneous method. Understood that part? Okay, so there is a very important point in this question now. So I like this question very much. I'll explain it nicely. So however, what is happening when you dissolve these things in acids? So these two iron oxides are broken and their ions are separated. Okay, so let's write it down. FeO with concentrated acid, it is converted to Fe2 plus. If you have Fe2O3, that is also converted to Fe3 plus. So now this solution is containing those ions. That means here you have Fe2 plus and Fe3 plus. Fe2 plus and Fe3 plus. So in the solution also you have the same ions. Fe2 plus and Fe3 plus. And now it is titrated with KMnO4. Okay, so during titration with KMnO4, KMnO4 is a good oxidizing agent. With that, the oxidizable ion is Fe2 plus. Fe2 plus is reacting. So by this titration, you can find out Fe2 plus moles. So however, Fe2 plus is converted to Fe3 plus during the titration. Okay, and then here we can't forget one thing. The important point I said is this one. So KMnO4 is reduced to Mn2 plus now. That Mn2 plus and Fe3 plus both are there. So when you increase the pH value by adding, to do that, you have to add a base, no? Sodium hydroxide or something. So then both of these two compounds will be precipitated. That means manganese 2 plus will be precipitated as manganese hydroxide. And iron 3 plus will be precipitated as iron 3 hydroxide. Okay, so the mass of these two compounds is 0.75706, not only Fe3 plus, okay? You have to consider Mn2 plus also. That is the interesting part in this question. Not only one, you have to consider Mn also. So I mentioned that one in the question. Let's go and check that one quickly. Here, I gave you the reaction. So these reactions are not given in the level exam. Okay, for you to understand, I mentioned this. So pH increasing means addition of sodium hydroxide. So Fe3 plus and Mn2 plus, all of them will be precipitate. They are asking balance chemical equations for the titration and precipitation reactions. Okay, so we need a redox reaction to balance here. Calculate the mass percentages of these two compounds. Yeah, okay. You'll see they have given the molar masses also. Okay, so let's start from this titration. So I'm going to do this one in two parts. Let's first of all find out the FeO number of moles. Okay. Here also you can go with XY thing. That is more convenient, but in the exam without XY you can do this because we are not going to use a simultaneous equation for this one. Because why? Here from this titration you can only find Fe2 plus moles. So that is kind of giving you exactly moles of one reactant. So no need to use simultaneous. Okay. So, but I will add an X and Y for you to understand more, right? So let's say the number of moles of this one as X and number of moles of this one as Y. So if they are dissolved in dilute acids or concentrated acid, it will give you 2Fe3 plus. Okay, 2Fe3 plus. So here that means here you have 2Y, here you have X. That means you have X and 2Y. Then X and 2Y are there, so it reacting with KMnO4. Okay, so now finally it is converted to Fe3 plus now. To understand this too, Fe2 plus that is there is converting fully to Fe3 plus during this KMnO4 reaction. That means if you had X moles, you will have X moles of Fe3 plus also from that. So that means 2Y plus X moles are there. Okay, so permanganate also you can find how many moles are there by that particular titration. Okay, so now let's start the question with KMnO4. Right, the first thing, moles of KMnO4 or MnO4 minus. Moles of MnO4 minus you can multiply 0.02 moles per decimeter cube into 20 into 10 to the power minus 3 dm cube. And you will get 0.04, 0.4 into 10 to the power minus 3 moles. This is the number of moles of MnO4 minus 0.4. 0.4. Right? And then we need to write the balanced equation between MnO4 minus and Fe2 plus. So now here manganese reducing to Mn2 plus and Fe2 plus goes to Fe3 plus. Remember our redox method? We need the oxidation numbers. This one is plus 7, plus 2, and plus 2 and plus 3. You can see this is oxidizing by losing 1 electron. And this is reducing by gaining 5 electrons. So the least common multiple between 1 and 5 is 5. So let's multiply this one by 5. So 5 Fe3 plus and 5 Fe2 plus. Now the electrons are balanced. 5 electrons lost, 5 electrons gain. Okay, 5 electrons lost, 5 electrons gain. Then let's balance the charges. Here it is plus 10 and minus 1 plus 9. And here it is plus 15 and plus 17. So 8H plus is missing. You can add 8H plus here. And then 4H2O. 4H2O. Understood? So what is needed for our simplification is this ratio. 1:5 ratio. Okay. So we can find out then moles of Fe2 plus. Moles of Fe2 plus is 5 times, 5 times like this number of moles. So 0.4 into 10 to the power minus 3 into 5. Okay. So 4 times 5, 20. So 2 into 10 to the power minus 3 moles. That is the number of moles of Fe2 plus. Fe2 plus. That means Fe2 plus is given by FeO. So FeO also you have the same number of moles. So moles of FeO is equal to 0. Or you can write 2 into 10 to the power minus 3. Now what we need is the mass percentage of FeO. So you can find molar mass of FeO. Molar mass of FeO. 56 plus 16 62 and 72 grams per mole. Then let's find out mass percentage of directly FeO. So let's multiply this 2 into 10 to the power minus 3 moles by 72 grams per mole and divide by the total mass. It is given 0.48 grams and multiply by 100%. Okay, multiply by 100%. So it is divisible by 12. 72 is 6 times 12. 48 is 4 times 12. So 0.04. And it is divisible by 2 also. 0.02. In A-level exam, don't use a pen to cut these things, okay, Lama? Use a pencil. Or do the simplification somewhere else. Using pencil is okay. And yeah, this also simplify. Can simplify 0 and 3. Yes, now it is 1030%. 30%. That is the mass percentage of FeO. So that's very simple actually related to the other part. Okay, so see whether you have any doubts on this one. Mama, I'll check our answer whether it is correct. 2022. Yes, it is 30%. 30%. Mass of FeO will be mass of this one if you find separately 0.144 grams. Right, so what is important for us? Okay, so we know the moles of KMnO4, which is 0.4 into 10 to the power minus 3. So that means Mn2 plus also you have 0.4 into 10 to the power minus 3 moles. And you know this X also, which is given by Fe2 plus later, that moles is also equal to 2 into 10 to the power minus 3. So you know those two moles. Okay. Yeah, they haven't mentioned, now one of you are asking a good question. They haven't mentioned that manganese precipitation, but you will learn in inorganic chemistry, the theory is needed to understand that, okay? So for right now, I have to tell you that Mn is precipitated, okay? But later lesson, you will realize how it is being a precipitate. Okay. Right, now this part is done. We found the mass percentage of one reactant, one compound, and now let's go and find the mass percentage of Fe2O3. So I'm going to erase this new part I wrote. Okay, done. Add this one to your, write this one in a foolscap or A4 sheet and paste this answer and the method, whatever the explanation you wrote, in your theory book. Okay, for calculation, I have given you a tute. In that tute, okay, paste this one. Then when you are studying for exam, when you study chemical calculations again, you can see that part. But when you want to study something, usually you don't look at the questions, you look at the theory book. So then you must add this one to your theory book. Like we did to the last two questions, okay? Yeah, this question normally you can take 30 minutes, up to 30 minutes for one essay. No? There are two parts in this inorganic question. This coming under inorganic calculation, and for the first part only like 10 minutes will be gone, and the other within other 20 minutes you have to do the question. So right now, if you are 27 student, it may be still difficult to do within 20 minutes, but let's practice. Okay, with the practice, you can do it. Now I have seen that is happening. Students are doing that one, so don't worry. Just leave that part for your practice and just understand the question and try it. Okay, so more you do, more you repeat the same thing, you will good at with the timing. Okay, so right now, don't worry about the timing. Focus on how to do the question properly. Okay, don't miss anything. I mean, balancing, units, and then small phrases, statements we write. So those things must be there. No? After knowing them properly, then you can think about the timing. Let's see. Let's see how that happens. Okay. Right. So next thing, we are going to find out the Fe2O3 mass percentage. Right now, here's we are going to start. Total mass we know, right? From that, we are going to do this question. So since we know the Mn2 plus moles, we have to write this reaction. So they are expecting you to write this precipitation reaction. So manganese hydroxide is precipitated. So if you had 0.4 into 10 to the power minus 3 moles, you will have 0.4 into 10 to the power minus 3 moles of this compound also. Okay, so that means we can find out mass of manganese hydroxide. So for that we need the molar mass first. Okay, molar mass of a manganese hydroxide. So manganese, I think they gave it as 55 relative atomic mass. 55. Check that one, Lama. 55. Yes, 55. See here. Iron is 56. So 55 plus 17 into 2. 16 plus 1, 17. That means 34. 34 and 55, 9, 89. So 89 grams per mole. Then we can find out the mass of MnOH twice. So just multiply 0.4 into 10 to the power minus 3 by 89. So 89 times 4, 36, 3, 32, 35. So answer is 35.6 into 10 to the power minus 3 or 0.0356 grams. Now this is the total mass now. So then by subtracting, you can find out mass of ferric hydroxide. So 0.5706 minus 0.0356. 5706, 356. Now 6 and 6 subtracted 0, and here it is 5, and 6, 3. Yeah, 0.535. 0.535. 50 grams. This is the amount of grams of moles of Fe, mass of ferric hydroxide. So now let's find out molar mass of ferric hydroxide. Molar mass of ferric hydroxide. Yeah, it is 56. 56 plus 17 into 3. 17 into 3. 7 into 3, 21. 30 and 56. 7, 107. So 107 gram per mole. Okay. So now we can find out the moles of ferric hydroxide. Moles of ferric hydroxide. So what should we do? Divide this 0.535 by 107. It is divisible. You should be happy. It is divisible because 107 into 5, check, 35, 535. See, divisible. So 0.001 moles. That is the number of moles of ferric hydroxide. But don't be rushing. That number of moles is included with this salts. Not 1, sorry, 5. 0.005. Okay, and here this 0.002 is also there. Okay, you understand that one? It's a very good question. See, kind of the best question, no? Out of the past paper 4 questions we did, 2019, 20, 21, 22. This one is much better. There is a long process, that's all. Okay, so now let's find out FeOH3 precipitated from Fe3 plus already existing. Fe3 plus from ferric oxide. That means 0.005 minus 0.002, 0.003 moles. So I have to mention that one also. I think adding one more statement is better. So you can write moles of FeOH thrice from Fe3 plus from Fe2 plus. That earlier Fe2 plus was also converted to Fe3 plus. You have to acknowledge that one here. So 0.002. That 0.002 is subtracted here. Okay. So now, if you know the moles of Fe3 plus, that means you know this part. That means it is equal to 2y. Remember, it is equal to 2y. So finally, we can go to moles of Fe2O3, which is 0.003 divided by 2, 0.0015 moles. And they are asking the mass percentage. So one more step to do. Find the molar mass and multiply it by the number of moles and divide by that value. So I'll show you that simplification also somewhere here. I think this one we can erase now. Simplification is this 0.0015. That is the number of moles of ferric oxide. And the molar mass of ferric oxide is 56 times 2, 112, 48, 160. And it's actually divided by 0.48 into 100%. So this is divisible. You can divide this one by 16. So it is 10. This one you can divide by 16, 0.03. Then 0.15 divided by 3, 0.05. Yes, 50%. 50% is the answer. So when you do the question at home, did you got that answer? Can I see a hand raise if you did so? 50%. Okay. Very good. So your method and approach may be different, but still, if you have these essential points, that is good. Okay. So that's it about the second question. Study this well. Study this well. And like I said, add a note about this question to your book. So this question is really, really interesting. Why? Because it is showing you that not only the Fe3 plus formed, okay, Mn2 plus that is formed during the titration is also precipitating. That's a very nice point, okay? And to that Fe3 plus, that titration is also giving Fe3 plus. No, that Fe3 plus is also there. So it's a very tricky question. It's a very good one to practice, okay? Just remember this whole thing. So I also remember, no? You can also do that. Don't worry. Right, so now we can move into our MCQ questions. So I added the answers written. There is a small problem with one question. Apart from that, others are, I think, you got okay. So I'm going to quickly discuss that 10 MCQs also. Now all these questions are true-false questions. True-false questions. So now about this question, if you didn't understand some part, if you have any further question, you can watch the recording again, or you can ask the doubt even in the theory class too. Okay, so don't keep doubts. Study. These are good questions. What I need you to do is practicing these questions more. Okay, at least after I explain the question, if you can do this with my help, that is also a better thing. Huh? Someday you can do this alone. Don't worry. Right, now let's look at these MCQs. See, sodium carbonate 1 mole per decimeter cube solution is more suitable to find the concentration of sulfuric solution than using sodium hydroxide 2 mole per decimeter cube solution. So now when you take the reactions, sulfuric react with both sodium carbonate and sodium hydroxide. So it's not a problem with the reaction. So the problem is one of these two chemicals is not a standard chemical, primary standard substance. That is the problem. So now, however, when they react with each other, they form Na2SO4 and H2CO3. Okay, and in inorganic lesson you will learn these products. Okay, or you can write Na2SO4 and H2O and CO2. That also applicable because H2CO3 can be written like water and carbon dioxide also. And here you know the product already. This we discussed under our calculation theory. So sodium sulfate 10 to water is formed. Okay, so that's the those are the reactions, right? But using sodium hydroxide is not suitable. Why? Because this is not a primary standard. Okay, the reasons are it absorbs CO2 and water vapor from air. Therefore, it is not typically pure. Okay, so that's why it is not a primary standard. Okay, so but this compound, it is not, it can't absorb water and it doesn't absorb CO2. So it's a good primary standard. It is a good primary standard. So that doesn't mean Lamai sodium hydroxide can't use for titrations. Okay, sodium hydroxide can be used to titrations. But first of all, you should find the concentration of that sodium hydroxide solution by doing a titration with a known solution. Okay, so if it is not a primary standard, this is the step you need to write. Before titrations, this should be standardized. Using another primary standard. And then this would become a secondary standard. Okay, sodium hydroxide will become a secondary standard. So then you can use it for titrations. Can be used for titrations. Remember that one, okay? So I'm not telling that even in the question also it is asked what is more suitable. So more suitable is sodium carbonate because you can directly use that, no? You can directly measure some mass of sodium carbonate and dissolve that in water. Okay, we discussed that practical also, preparing a standard solution. You can follow that procedure and make a standard sodium carbonate solution and do the titration without any problem, without any worries, right? But if it is a sodium hydroxide, you need to follow this procedure. Right, so first statement is correct. First statement is correct. And then the second one, sodium carbonate is a primary standard, while sodium hydroxide is not a primary standard. That is also correct. And it can explain the first statement also. Therefore, your answer will be what? Your answer will be answer 1. If it can explain the first statement, answer will be answer 1. Yeah, I got some responses. We will see how you have performed. Ashia. See? Yeah, out of the students who answered, yeah, majority selected the answer 1. Very good. Okay, now let's move to the second question. The IUPAC name of the compound Fe2S3 is ferric sulfide. Ferric sulfide. What do you think? Is it the name? Is it the IUPAC name? If it is IUPAC name, you don't use this Latin name. Okay, you are using the English name with Roman numerals. If it is Fe, you have to say iron, IRON. Iron 2, iron 3, that is the way. Iron 2, iron 3. So this is called a trivial name, not the IUPAC name. See, these things can be there in your tests, okay? So the IUPAC name of the compound Fe2S3 is not ferric sulfide. Ferric sulfide is a trivial name. Fe2S3, ferric sulfide, you are using simple letters. Ferric sulfide is the trivial. But IUPAC name is what? IRON, iron 3, iron 3, sulfur, space sulfur. This is IUPAC name. So remember that one. So the first statement is wrong. First statement is wrong. And there is another error. Did you see it is not even a trivial name also? Why? How can you see the way that they spelled sulfide? That is also wrong. How should you write the name? SULF, sulfide. F should be used. For the nomenclature, sulfide is also correct. PHIDE is also correct. But for the nomenclature, you have to use F. Remember that point. So therefore, first statement is anyway a wrong one. There are two mistakes. One is it's not the trivial, it's not the IUPAC name. Other mistake is the sulfide, the way of writing sulfide is wrong. Okay, write those 2 points for your reading. And then look at the next point. In the compound Fe2S3, iron exists in the +3 oxidation state. It is true. It is true. If I just explain a little bit more about the compound. So this one is composed of Fe3 plus and S2 minus. It is just similar to Al2O3 you learn in O levels. Remember, how did you form the formula? Al3 plus was there or 2 minus was there. So 3 and 2. Then you change the valencies, no? Then it will be it became Al2O3. Just like that, there you have Fe3 plus and S2 minus. So oxidation number is equal to the charge. So it is plus 3. Second statement is true. So first one correct, first one wrong, second one correct. Answer is answer 4. Let's see how many of you got that one. See, can you see that? So some of you got wrong there. That means you need to focus more on that one, no? So this is like I said earlier. So in the very early paper classes, we did this Google Sheet thing. So from this week onwards, I am resuming that part again. So it will give you an idea regarding what is the majority answer. Okay, so then you can get some evaluation about yourself. Okay, so some of you selected 1 and 2 because they thought that first one is correct. So now those who marked first one as correct one has to understand why it is wrong. Okay, understand it properly. There are 2 mistakes in the name. First one, it is not a IUPAC name, and second one, the way of writing sulfide. Okay, right. Now let's go to the third MCQ. In third MCQ, it says in acidic medium, potassium permanganate reacts with, in acidic medium, potassium permanganate is reacting with copper 1 sulfide in 2 to 1 ratio to give copper 2 plus SO4 2 minus and Mn2 plus. So here I just try to check your nomenclature knowledge together with the redox knowledge, redox reaction balancing knowledge. Okay, so what is this copper 1 sulfide? Copper 1 sulfide. Copper 1 sulfide. Copper 1 sulfide is, here you have copper plus and sulfide is having minus 2. So if you write the formula, it will be Cu2S, copper 1 sulfide. Okay, CuS is copper 2 sulfide. Remember, when we do the lesson, we did that part, no? And the copper 1 sulfide, copper 2 sulfide, right? Then it is reacting with KMnO4. So Cu2S is reacting with KMnO4. We take the MnO4 minus only because that is the that is the reactive part. K plus is an spectate ion. So now it says it is the products are Mn2 plus and sulfur is going to SO4 2 minus and copper is going to copper 2 plus. So now if you check the oxidation numbers, here you have plus 1 copper 2 atoms. So the oxidation number is cumulative oxidation number plus 2. Here sulfur minus 2. Manganese plus 7. Here it is plus 2, plus 6 and plus 2. But here you have to put 2 in front of this because there are 2 copper atoms. So 2 into 2 plus 4. Okay. So what you can see here, while KMnO4 is undergoing reduction by taking 5 electrons, both of these sulfur atoms and copper atoms are undergoing oxidation. Remember the word double redox we learned? Double redox. So both entities are undergoing oxidation. Okay. So here it is from plus 2 to plus 4 copper. That means it is losing 2 electrons. What about sulfur? Minus 2 to plus 6. Minus 2 to plus 6. Minus 2 plus 6. See, gap is 8, no? So it is losing 8 electrons during the oxidation. So altogether, both of them have lost 10 electrons. 10 electrons. So while 10 electrons are gaining, 5 electrons are gaining, 10 electrons are losing. So to balance the electron exchange, you need to multiply this one by 2. Okay, so 2 MnO4 minus and 2 Mn2 plus. Then you can check the charge. Here it is -2. Here it is 22 plus 4 plus 8 plus 6. And you can put 8H plus. 8H plus and forward. Check the oxygen atoms. Here you have 8 oxygen. In that side also 8 oxygen. So this equation was there in 2020 A-level chemical calculation essay. We did that one in the class. In that essay question, I explained the balancing in the board also. Right? So now what is the ratio between these two? Copper 1 sulfide and permanganate. What is the ratio? 1:2 ratio. Now, is that the ratio it is given in the book? You given in the question. Check that one. Yeah, 2:1 ratio. Potassium permanganate reacts with copper 1 sulfide. So potassium permanganate is mentioned first, no? So that means 2:1 ratio. Correct. First statement is correct. What about the second statement? Potassium permanganate is a good reducing agent. So what type of an agent is permanganate here? Permanganate undergo reduction. Therefore, MnO4 minus is oxidizing the other entity. No? So permanganate is a good oxidizing agent. Oxidizing agent, not a reducing agent. So first statement is correct, but the second one is false. Answer is answer 3. Okay, so it's a good question. Basically, I prepared the question, but the theory points I took from our previous discussions. Okay, so everything we are discussing here, you are being taught. Okay, see the answers again. A clear variation is there. That signals us what are the mistakes, what are the things we need to develop. Right, now let's go to the next one. Fourth question. Now these first 3 questions are from chemical calculations, and the next 3 questions are from gases, the lesson we just started. So we did only one theory discussion, 1 day theory discussion for gases. Okay, so these 3 questions are asked from that. Right, look at the first one. Look at the first one. First one means the fourth question. At suitable temperatures, ideal gases can be liquefied at very high pressure. And ideal gases have weak intermolecular attractions. Now let's go and check your answers for this one. I'm curious. So here both statements are wrong. Okay, very good. 4 of you have taken that answer. Some of you are misguided. But however, good. Better than I expected. At suitable temperatures, ideal gases can be liquefied at very high pressure. So why it is wrong? Because the first statement is wrong. Why? Ideal gases have no intermolecular attractions. Okay, so then they will not be liquefied. Okay, so therefore not liquefied. Only real gases are liquefied. For real gases, this statement will be true. Okay, liquefied. That also you have to compress at a temperature below critical temperature. Remember this phase diagram we learned? This is your triple point and this is your critical point. This is your critical temperature. If you compress the gas at a temperature lower than the critical temperature, then it will be liquefied. Okay, but if you are compressing it after the critical point, not liquefied. Remember that point also. If the temperature is greater than the critical temperature, then it is not going to be liquefied. So look at the statement. It is telling that suitable temperatures or something. Ne? Yeah, suitable temperature. So this first statement is true for real gases, but it is not true for ideal gases, because ideal gases are not having at least weak attractions. They have basically no attractions. No attraction. So first statement, second statement, both are incorrect. Is that clear, Laman? So answer is answer 5. A good question. Then look at the fifth one. At room temperature and atmospheric pressure, CO2 solid or dry ice undergo sublimation without giving a liquid state. Yeah. So it undergoes sublimation. There is a small problem with the question, Lama. When I'm preparing the question, I didn't thought about that much. So here the problem is I added the both conditions, room temperature and atmospheric pressure. Now here you need to correct this thing. So anyway, I'll give you the printout in our next class. I'll correct that thing when I'm giving this. Okay. So at room, if I say only at room temperature, or if I say only at atmospheric pressure, this is enough. So I think the better word to keep is atmospheric pressure. So let's erase this room temperature. Okay, so then think, okay, under atmospheric pressure, carbon dioxide is undergoes only sublimation without giving a liquid. That is true. So then in the second statement also, you have to remove the room temperature part. Then you can say at atmospheric pressure, solid CO2 is coexisting only with gaseous CO2. So then you have to assume that you are removing the two words. Okay, keeping these two words will give you a very confusing answer, though. Just ignore that one. Let's remove the at room temperature part. Okay, then you can get the correct answer. Understood that one? So at room temperature, that part you have to cut. Okay, so then at atmospheric pressure, keep that word. So now this is our carbon dioxide phase diagram. Pressure, temperature. This is the triple point of carbon dioxide. Triple point pressure is 5.1180. Remember, you don't really need to memorize that one. No? So, but we are living in 180 impression. 180 impression. So that means in 180 m, you can only see the solid state and gaseous state. So you don't see any liquid state. Liquid state existing after the triple point pressure. That means after the 5.11 pressure. That's why in our normal conditions, we don't see CO2 liquid. Okay, just erase the two words. Then you will get the answer as answer 1. So you remember there was a question in last year 2024 A-level MCQ. We did that question in the class. So refer to that explanation again. Huh? So coexisting means at equilibrium. Coexisting means equilibrium. One of you are asking, a friend is asking, do we need the both temperature and pressure to arrive any conclusion? But we don't need to. Here you can see. Only pressure is enough. Here variable temperatures, but at a constant pressure. To build the question, giving pressure is enough. Okay. Okay, so some of you noticed the problem with the question, and they put a message also asking, is there any problem with the question? That's really good. Okay, so that means you are kind of being aware with the questions now. That is very good. I had to appreciate that. So like I said, there are very good students with us. So practice. Okay, fix your problems and you can get an unexpected results. Okay, when you wouldn't believe your result. I mean a result in a good way, right? Right, so look at the sixth question. Critical temperature of N2 is higher than that of ammonia. So critical temperature is the temperature, the maximum temperature where liquid and gas phases are at equilibrium. After that, there is no equilibrium, liquid gas equilibrium. So you will have a, you will not have that interface. I explained that point. We will tell it again. So anyway, in the sixth question, it is comparing the critical points of ammonia and what is the other compound? N2. Ammonia and N2. So here's the thing. Critical temperature indicate the strength of intermolecular attractions. Okay. So let's say if the intermolecular interactions, if intermolecular attractions are strong, if intermolecular attractions are strong, your critical temperature is higher. That means what? That is the meaning of that thing. Just don't remember everything, right? Just try to understand. If you are having a higher critical temperature, that means you can that solid liquid gas equilibrium can exist for a longer temperature range. Okay, that means even at a higher temperature, you can compress and make it into a liquid. That is the idea. So that means the attraction force is supposed to be stronger, isn't it? Just think about that one. So here ammonia is the one with better interactions now. Ammonia is having hydrogen bonds, but N2 gas is having just London forces only. Ammonia is having hydrogen bonds, London forces, everything. So that means good intermolecular attraction. So if you get an ammonia gas sample, even at a higher temperature, you can compress that sample and convert that gas sample into a liquid. You can do that. Understood that. But you can't do that same thing with what? N2. Because N2 is having weak attractions now. So at sometimes at higher temperatures, if you compress, it will not be liquefied. Because the attraction forces are not strong enough to make it into a liquid. Try to understand that point. Okay, so that's how intermolecular attractions can represent critical temperature. Okay, so here, look at the statement again. It says, critical temperature of N2 is higher than that of ammonia. So it's wrong. Critical temperature is higher in ammonia. You can write the interactions to the review. Ammonia is having H bonds and London forces. Nitrogen N2 is a nonpolar molecule. So it is having London forces only. Okay, so therefore it is weak. That means weak intermolecular attractions. So your critical temperature is low. Critical temperature is low. Look at the second statement. Relative molecular mass of N2 is higher than that of ammonia. That is true. For relative molecular mass, if you go, N2 is having 2 nitrogen atoms. So 14 times 2, 28. But ammonia, relative molecular mass is just 70. 14 plus 3. That is true, but it is not relevant. Anyway, the first statement is wrong. So answer is answer 4. Let's see how many of you got answer 4 for the sixth question. Yes, very good. See? Yeah, then look at the next one. Question number 7. Now 7, 8, 9, 10, those 4 questions I gave you to just to make sure that you remember our first 2 lessons. Atomic structure and bonding. Our previously concluded evaluation test discussion also contains several good questions. Actually 35 MCQs from these 2 lessons mainly. Okay, maybe 30 or 28 or some questions are there from these 2 lessons. So basically in that evaluation test, we revised the whole syllabus we have completed up to now. So please refer that one and write your review, complete that review. So it's fully completed now. So what you have to do is your responsibility. complete the preview of that paper. So now look at the 7th question. Removing an electron from gaseous phosphorus atom require more energy than removing an electron from gaseous sulfur atom. Okay, so let's see. Removing electron in gaseous state means it is first ionization energy. First of all, you have to understand that. So if you take phosphorus gaseous atom, you remove one electron, it will become P plus 1. Okay. And the other one they are comparing here is sulfur. Sulfur plus. So, you know the ionization energy of phosphorus is higher than sulfur. Why? Remember this variation. Phosphorus, sulfur, chlorine, argon. And here you had the silicon. It's continuing here. So why this phosphorus is having higher value? What is the reason? Because phosphorus is having stable NS2, NP3 stable electronic configuration. That's why. That is the reason that phosphorus is having higher ionization energy. Okay. So ionization energy of phosphorus is higher than first ionization energy of sulfur. That is correct. So first statement is correct. But look at the answer they have given, the reason they have given. That is not acceptable. The effective nuclear charge of phosphorus atom, phosphorus is higher than effective nuclear charge of sulfur. Effective nuclear charge is higher for sulfur. Okay, so that reason is wrong. Why? Because ZEFF increases across the period. With increasing nuclear charge. Okay, as the nuclear charge increases, effective nuclear charge is also increases. So sulfur is having 16 protons, phosphorus is having just 15 protons, right? So obviously the one with more protons is having more nuclear attraction, more effective nuclear attraction also. Understood? Effective nuclear charge, whatever, right? It is higher. So second statement is false. Look at the question again. First one is correct. Second one is wrong. So what is the correct explanation for the first statement? You have to talk about their stable electronic configuration. Okay, write down that. So seventh one, let's see how many of you got it correct. Okay, very good. Yes. Yeah, some of you had mistakenly select answer 1 also. So those students has to focus more about that point I just said. Understand, learn from your mistake. And very good, more students have selected the answer 3. Very good. Now let's look at the question number 8. Right, then look at the next. Carbon-hydrogen bond length of ethene is higher than the carbon-hydrogen bond length of ethyne. Anyway, I gave you the formula also, so you can build the molecule. Ethene is this one. Ethene. And ethyne, you have a carbon-carbon triple bond. Ethene, ethyne. So there they talk about the carbon-hydrogen bond length. Okay, so now if you just look at the molecule, you will see only one single bond. So sometimes you might think, is this same length? Huh? No, it's not going to be the same length. Why? Why I'm telling that? Because here the orbitals participated for the hybrid bonding is different. From hydrogen, 1s orbitals are participating always, but here this hybridization is sp2. This hybridization is sp. So here you have sp2s overlapping, sp2 1s overlap. Here you have sp and 1s overlap. So what you know is, right, sp3 orbitals are longer and sp2 orbitals are really shorter than that. And sp orbitals are even shorter than that. So when the bond length, orbital length decreases, the bond length is also decreases. So this one is having shorter bond length. Understood? That is the reason. Now let's look at the statement. First statement tells ethene is having higher bond length. That is true. Second statement, yeah, the hybridizations are wrong. It's not sp3, sp2, it is sp2 and sp. Okay, first statement correct, second one wrong, answer 3. Let's see how many of you got the answer 3. Okay, very good. Majority has selected answer 3. Some of you have selected answer 2 also. That means 2, 1. They have missed the hybridization. So it's a careless mistake, Lamai. Just look at that carefully. Now you will understand it. Okay, so they are doing these things in the exam because after passing, A levels properly, you are selected to, most demanding professions, isn't it? Basically, we can call that not the degree, just focus on the profession. To become a doctor, to become an engineer, there are many other good professions along with that, right? So they are highly demanding. So then you need to be well focused. You have to pay attention to even for small details, like you have to have that skill, right? So if you are doing mistakes here, it's fine. You have plenty of time until the exam. Just try to make those mistakes correct, right? With more practice. Okay, for that, the easiest way is writing good reviews and doing questions like this. Right, so answer is answer 3. Now go to the question number 9. It says hydrogen emission spectrum question. Okay, so I try to cover basically the whole thing. I'll do the same thing in your next week class too. Hydrogen emission spectrum. Electron transition from 5 to 2 is higher energy than the electron transition from 2 to 1. Okay, let's 5 to 2 and 2 to 1. 5 to 2 and 2 to 1. So let's draw 5 energy levels. Second one, third energy level, fourth energy level, and fifth energy level. 1, 2, 3, 4, 5. And here, 5 to 2 transition. Here you have the 2 to 1 transition. Now, technically, we should be having high energy. Like this, isn't it? So, always remember, okay, so those are falling to first energy level belong to the Lyman series. Any Lyman series line is there in UV region. UV region means high energy. That's the way you have to think. Any line that is falling second to the second energy level is there in the Balmer series. Balmer series. Balmer series first 4 lines are there in the visible region. So this is also there in the visible region. So you can say 3 to 2 is red, 4 to 2 is green, this one is blue. This is the blue color line. Okay, so visible is having relatively low energy. So first statement is incorrect. It doesn't matter how many energy levels are there in between. It is just matter what is the total energy, not the number of energy levels. It's a good point. It's a very common point that people miss. So first one is wrong. Look at the second one. Energy level has higher energy than the first energy level. Yes, second energy level is having a high energy. Who says no? It is correct. If you move away from the nucleus, energy increases, but the energy gap, the difference, energy difference decreases. Okay, so answer 4. Okay, very good. Most of you have selected that answer. Right, now let's go to the last MCQ. Last MCQ. Bond angles of CO3 2- are identical. bond angles of CO3 2- are identical. So what do you think? So this is the carbonate or CO3 2- ion. So it's a Lewis structure. Don't forget that. Real carbonate is a resonance hybrid of these three Lewis structures. There is another one coming. So you have to show lone pairs in order to be true. Okay, real carbonate is a hybrid of all these three. That means it's like this. So bond repulsion units are same. Repulsion units are equal type. So their repulsion is same. Repulsion is same. Repulsion is same. So therefore bond angle is exactly 120. Understand? So no difference. If you just look at this one, you might think this is pulling more repulsion and bond angle is changing. No. You have to focus on the hybrid. Okay, resonance hybrid. According to the resonance hybrid, bond angles are same. That statement is correct. So a common point, I think we discussed that several times in our class. So look at the second statement. In carbonate time, electron pair geometry around carbon is trigonal planar. Yes, that is correct. But can it explain about the identical bond angles? No. To explain the identical bond angles, you have to talk about the resonance hybrid. At least you have to say real carbonate or carbonate is a hybrid of three resonance structures. Like that, you have to say something about that, not about the trigonal plane. Understand? Not about the trigonal plane, but look at this one. SOCl2. So this is also trigonal plane or no? Not this one, COCl2. This is also trigonal plane or no? But bond angles are not equal. So telling trigonal plane is not an explanation. Okay? So answer is answer 2. Yeah, some of you have selected answer 4, 1 also. I think because of that mistake. Answer 4 means second one is wrong. Why second one is it wrong? Trigonal plane and it is trigonal. No, first one is wrong. Yeah. First one is not wrong, Lama. Yeah, it is correct. Bond angles are identical. That means those who selected answer 4 haven't focused about the hybrid thing. Ne? See, you can learn. Okay, so write a good review. We didn't do this part from a while. So answer checking and this discussion. It's a good thing. Let's start over that again, right? Okay, so I'll give you a printout of these questions in your next class along with the next week paper. Okay, so study well, Lamai, write a good review. Okay, so if you have further doubts about any question we discussed today, you can personally ask that in the class. Don't worry, ask everything and clarify your doubt. That's the most important thing you can get from me, because theories, everything you can watch from YouTube videos, you can read books and understand. But if you have a doubt, you need a teacher to clarify that doubt. Someone has to tell you this is your mistake, this is how you should do, right? That advice you have to get from me. Okay, that's where I come for your result. Okay, that's my role. So think about that too. So study well, write a good review. See you again in next week too. Okay, so goodbye, good night.